Professor Young-Duk Kim from Kyung University, and he's gonna talk about Moire, Exciton, Polariton for the quantum simulation. Okay, let's. I guess the speaker is on site. Okay. Let's welcome the speaker together.
Yeah, thank you for the introduction. First, I really appreciate to the organizer to invite me to the NIST conference, and then give me the opportunity to present our recent proposal to the NRF and the Air Force joint program. So today I'm gonna talk about the 2D semiconductor-based Moire varieties, Exciton Polariton for quantum simulation. I skipped the first slide. So previous speakers mentioned about the 2D material-based universal quantum computing, and then some graphene-based Singaporean detector, and then 2D material-based quantum emitter. So many people, many researchers realized that 2D van der Waals materials become our emerging quantum material for the quantum computing. So the upper part is traditional quantum material for the quantum simulator and the quantum emitter, and then the qubit system. And the bottom part, the lower part, is corresponding 2D van der Waals material for the quantum simulator and the defect state in the 2D semiconductor hexagonal nitride for the quantum emitter, and then some 2D superconductor for the high quality of the Josephson junction, and then superconducting qubit. So due to this kind of the reason, so NRF funding international research network for 2D van der Waals material-based quantum computing. So our team was organized by the Professor An of the University of Seoul. This program is encouraging of the strong collaboration with the Korea researcher and then the overseas researcher for the developing the new concept of the quantum computing. So our team is focused on the 2D van der Waals materials. So our overseas researcher include Philip Kim at Harvard, and the Bino Menon at the 6NY, and then Tony Rowe at the University of Minnesota, and then Berg Engelett at the NUS. So we are exploring the possibility of the 2D material for the next generation quantum computing and then quantum information. So our Seoul Center for Quantum Computing, so website is here. So you can, we sharing some information and then several seminar. If you are interested, please visit our website. So one of the our teams, including Bino Menon and then me and then Jae Jung, so we proposal to the developing of the 2D semiconductor with twisted Moire varieties. This material is embedded in the strongly coupled cavity mode. So maybe possible to developing some solid state quantum simulator. So Professor Bino Menon is working on the Exciton Polariton, and I am working on the heterostructure van der Waals device, and then Jae Jung is working on the 2D superlattice band calculation. So we developing this thing for the quantum simulator. So quantum simulator is several platform already developed. One of the example is a cold atom with optical lattice, and the trapped ion and the photonic circuit. So quantum simulator should be the first developing before the realization of the universal quantum computing system, because the quantum simulator don't need the quantum gating and the error correction. Is a more simpler structure. So based on this kind of the systems, so we can learn and simulate the many-body quantum simulation and solving the ground state of the Hamiltonian. So to developing quantum simulator, so for example, coordinating system, so there is some requirement. The first is we need the quantum matter. So in this case of the Polariton, so rubidium atom become some quantum matter, and then so we have to arrange this quantum matter as a periodic potential or some lattice structure. So in this platform, so they using the optical lattice, and then so third is we need to the manipulation of the quantum matter and the measurement of the quantum state. So this third requirement is very essential for developing the quantum simulator. So our system is first quantum matter will be the cavity exciton polariton. The cavity exciton polariton is we put the semiconductor between the 2 meter. So if photon is injected, semiconductor created the electron pair, and then after that, the radiative recombination emits the photon. This emitted photon also reflected again to create the exciton again. So if the this exciton and then cavity mode coupling is strong enough, they become a complex boson. It means the half of the exciton and the half of the photon. So energy dispersion relation is without any strong interaction. So exciton mode and the cavity mode is indicated by dashed line. But they have a strong coupling rhythm due to the quantum repulsive effect. They have 2 branches. So lower part is a lower Polariton bridge, and the upper part is upper Polariton bridge. So in the case of the non-resonance excitation of this Polariton is naturally condensated to the lower Polariton, so they stay at the ground state, and then they emit coherent light. So composite boson of the cavity exciton polariton is very interesting because they have a photonic feature as well as an excitonic feature. So it means they have a very small effective mass and high coherence. The long range measurement is as possible, and then so it also have a matter feature. So they also have showing very strong nonlinearity, and then very easy to manipulation of the exciton and the control of the interaction. So cavity exciton polariton system is a solid state based photonic quantum simulator platform. So we can manipulate the quantum matter using the solver method. It means that we can control the energy, momentum, polarization phase, and then we can detect each quantum state just prove the photon, leakage photon using the solver spectroscopy method. So this cavity exciton polariton mode in the gallium arsenide. So already 20 years ago, so people already demonstrated the quantum simulator system. Due to the high quality MV growth technique, they can growth of the high quality of the DDR cavity, and then embedded some multi-wall quantum well. So in this case, structure is so they provide a high quality of the strong coupling rhythm, and then according to this result under the high laser optical excitation, they observe the condensation at the lower Polariton bridge, as well as a Bose-Einstein condensation at the low temperature. So this gallium arsenide exciton Polariton quantum simulator, so we need to also manipulate the lattice. So one method is deposit the metal with the periodic hole. So due to the electrostatic potential difference, they can making the localization of the exciton at a certain position, and then they making the localization and then measuring energy dispersion. Another method is to just etching out all the gallium arsenide heterostructure and then form the lattice structure. So, but the problem of the gallium arsenide-based quantum simulator is gallium arsenide exciton binding energy is quite small, around 10 millivolt. So it only operates below the 10K, and then its Bohr radius is quite large, and then quantum simulator radius size is micron scale. So our team will using the 2D semiconductor. Why 2D semiconductor? The first, 2D semiconductor have a very large binding energy around the 100 to the 500 millivolt. As compared with the exciton binding energy with the gallium arsenide and other semiconductor and the 2D semiconductor, 2D semiconductors exciton binding energy is larger than room temperature, and then or their binding energy is easy to engineering by the just control of the substrate dielectric constant. And then 2015, Manon group, they put the molybdenum on the DBR cavity. And they first observed that exciton Polariton mode is possible, and the Rabi splitting is around the 46 millivolt. And then the first demonstration is creation of the exciton Polariton is only using the optical excitation, but 2019, so Manon group also using the electron injection, they also demonstrate electrical driven exciton Polariton is possible, and they're working at the room temperature. So large binding energy and the high temperature operation is a big advantage compared to the gallium arsenide. And then another advantage of the 2D semiconductor is we can using the valid degree of freedom. Also, charged exciton is prion. We can easily manipulate it and guiding with the electro gating. Another degree of freedom is we can also use interlayer exciton to increase the condensation temperature. So we need the lattice in our system. So we will using the Moire lattice. So 2D material is very free to making the heterostructure without any restriction of the lattice mismatch. And then even we can also control the angle between the two layers. So as you see this figure, when we change of the angle, you can see the change of the Moire wavelength. The 2018, the Pablo group at the MIT demonstrate their magic angular twisted graphene show the multi-insulating phase as well as the superconducting phase. And then, so this phase diagram is very similar to the high tissue cuprate superconductor phase diagram. And then after this, so people realize that, oh, this kind of the Moire lattice is could be the high tissue superconductor quantum simulator with the transport method. So we using the same concept. So we will using 2D semiconductor with a small angle mismatch, and then we form this kind of the Moire pattern. And then Moire pattern, due to the interlayer exciton interaction, they naturally form the local potential minimum, and the exciton will condensate at the minimum potential. So normally potential minimum is 100 millivolt, and we can easily manipulate by electrostatic gating. And then another advantage is we using the interlayer exciton. They have some very long lifetime around the millisecond. It means allowed to we measuring the we realize the quantum simulation system relatively high temperature above the liquid nitrogen. Yeah, so this is a measurement method I mentioned before. So gallium arsenide already quantum simulator using the real space imaging for the real space wave function distribution. And then if we're using the Fourier spectroscopy, we can also get the momentum energy dispersion. And then if we making set up the margin interferer, we can also get the phase information. So this is a kind of measurement scheme is relatively easy. And then Manon group also have this kind of spectroscopy setup. So our ultimate goal is making the 2D Moire lattice with the quantum simulator. So we will using 2D Exciton Polariton, and the lattice is we will using the Moire lattice. So when we compare with the real crystal structure, so real material is length scale is around angstrom, and the cold atom and trapped ion optical lattice length scale is a micron scale. So our system will be the length scale should be the nanometer to the 100 nanometer. It means we can study the many body quantum interaction system. For example, over the 1,000 quantum metal interaction is can observe that using our system. So our 2D semiconductor Exciton Polariton. So we will form the Exciton Polariton with the Moire pattern with something like this kind of structure. But there is a lot of the parameter to control the localization or tunneling, just a change of angle or electrostatic gating or apply to the pressure. And due to the, they also have exponent mode, so they also showing some nonlinear effect. Maybe we can achieve the Polariton blockade rhythm also possible. And then, so just using the hybrid photonic crystal with the boron nitride, we can achieve the more strong rhythm is possible. So our approach to programming the 2D semiconductor Exciton Polariton quantum simulator. So a simple strategy is a change of the angle when we're stacking the device. So we have a homemade automated van der Waals stacking device system. So we can control the angle below the 0.0002 degree. And then we also using the piezo manipulators, XYZ alignment is resolution is around 30 nanometer. And then also so using the evenly nano patterning, so we will get precise control of the angle of the device. So another strategy is using the AFM tips, we can continuously control the angle, and then we can measuring and then changing of the interaction. So another approach is we will making the in situ MEMS motor, so to control the precise angle without to bring out the sample from the measurement setup. So so far, so this kind of the super lattice is lattice structure is determined by the atomic crystal structure, but sometimes we need an arbitrary lattice structure. So Corridine and Philip also demonstrate that graphene with periodic patterned dielectric also making the realization of the super lattice structure in the graphene. So this is a strategy also working on the 2D semiconductor. Just arbitrarily patterning the lattice with the dielectric, we can making the arbitrary programming quantum simulated with the device is possible. So summary is that so 2D Moire pattern is provide a lot of the freedom such as Kagome lattice and the Majorana, fermion, and the quantum magnet. So, and then so they also allow the knob for change of angle gating, strain pressure, temperature. So maybe so quite stable and robust quantum simulator can be realized using the 2D semiconductors. Thank you for listening. Thank you.
Thank you very much. Thank you for a very inspiring talk. So now the session is open to the questions. So there are questions from the chatting room. The Young Kim asked, do you have any particular Hamiltonian to start with your simulation?
First, the first we will testing the Hubbard model. Yeah, so as like a gallium arsenide based quantum simulator, we define the lattice and then control the electrostatic gating. So we can actually prove the localization and then some DCS phase using this kind of structure. Yeah. First, we will try to the Hubbard model.
The next question is from Professor Jae-Young Kim. Unlike the optical lattice, even though some programming is available with the Moire lattice should maintain certain periodic property. Can it do simulation arbitrary lattice?
So this Moire super lattice always have this kind of some hexagonal or triangular lattice structure is realized, but sometimes we need to suffer sometimes we need to the 1D lattice or some 2D lattice or some cubic lattice, rectangular lattice. So in this case, it is hard to realize with Moire super lattice. So in this case, we can using some directly substrate patterning as like a graphene super lattice structure. Yeah.
Okay. Thank you. Thank you for answering. Okay, so